Processing data and statistical testing are one of the most important parts of a piece of biology coursework, but also where so often people get unstuck staring at a spreadsheet. So this video will walk you through how I would go about processing results for the three most common types of investigations and their statistical tests, smashing our way through Excel. And while this is applicable to all kinds of courses and experiments, we're particularly making sure we hit all the requirements for the updated 2025 IB biology specification. So if that's why you're here, you've nailed it. Let's do it. Okay, so we're here in Excel. I'm going to break this up into three major sections depending on which category your research question falls into. So before we start, pause the video, make sure you're clear on whether you're looking at a difference between two means, a correlation between two variables, or an association between two variables. I'm going to show you how I would set my results table up in Excel and how I would process these data. So that'll include the graphing and statistical testing as well. So let's jump straight into some differences. This is possibly the most straightforward of the data processing, and certainly the fewest steps. And this is how I would expect this to be set up in a spreadsheet to make life easiest for us. So just as a sort of model investigation here, I've been looking at limpet height. I've got two different sites. I've collected 20 bits of data from each site. Now that's not enough. The expectation here would be that you would have somewhere between 50 and 100 data points from each site, depending on what you're measuring. So something like limpet height, it's quite quick to measure. We should be getting a really big volume of data. If you're looking at something like a height to width ratio, obviously that takes a little bit longer, and so possibly you wouldn't get quite as many, but essentially collect as much data as you can and make these columns as big as you can, and therefore the most likely that you'll get some reliability in your results. So what we've got here then is two columns of data. This is just raw measured data. You can see these are just numbers in here. I have then put two columns next to those, which I've titled RM. That's for running mean. So the first thing that we need to make sure of when we have our data set is that we have sufficient data. To demonstrate and justify the fact that we have sufficient data, we're going to calculate running means. This is a really straightforward bit of Excel work. So we're going to come into this cell here. What we want each cell in this column to return to us is the average of the data point we've just taken and every data point up to that point. So this cell here, we want to return the average of these four data points. To do that quickly, we're going to put in the top cell here, equals average. That's going to start returning means to us. And now for this average is obviously just going to be the average of that cell and no others. So we'll just do B3 to B3, close that bracket, hit enter, and that will give us an average, which is exactly what that cell is. We're going to want to drag this down and copy that formula into all of these cells. Before we do that, we're going to need to add a dollar sign. Dollar signs in Excel lock a variable, so either a column or a row, so that it doesn't change when you copy the formula. In this case, we want to make sure that the first cell in our range is always B3, and so that when we drag this down and we extend it, we'll get B3 staying the same, and then the last data point will change. So we're going to put a dollar sign before the 3 rather, and that's going to lock that number B3. This second B3 will then change as we copy the cell, depending on where that cell has been copied to. So hit enter on there, and that won't change the result. If I select this cell now, you can see this little green box down in the right-hand corner. When you hover over that, your cursor will change from the big white cross to a small black one. That's going to be our cell copying drag. So if we click there and drag down, that will fill by default all of those cells with the formula from the top cell. And you can see for each of these then, this is calculating the mean of the cell to the left and all the cells above it. There's a little green triangle in the corner there. That's going to return a little error, which is that adjacent cells are not included in the average. You can see that in here. As the formula omits adjacent cells, that means that it's just warning you that that average is not including a number that's next to that cell. That's fine. That's exactly what we want in this case. So if it bothers you, you can highlight them all and ignore the error, and it'll disappear. We then want to do exactly the same over on this side. So that's really straightforward. We can just copy that cell and chuck it into there, and that's now going to reference D3, which is the right column for that. Again, we're going to hover in the right-hand corner, little back square, click and drag that all the way down. That's generating a running mean, again, we're getting that little error, which I will click. Okay, so that's our running mean. Now to justify that we have sufficient data in here, by standard, we're going to look at the last 5 of the running means, and we want to demonstrate that there is less than 5% deviation within each of those running means. So down here, I've just put a little row in for stability, and that's showing, or that's going to return whether we have a stable running mean or not. So in this cell here, I'm going to use a formula that will give me the percentage change or the proportional change between the minimum and the maximum value within the last 5. So formula we're going to want in here is equals max. I'm just going to return the maximum value from these 5 square open brackets, and then select those 5 cells, so the last 5 in your running means, and close that off. And we're going to divide that by the minimum, so min, open brackets, same 5 cells, close the bracket off, and that will give us a result somewhere between 1 and 1 upwards. What this is telling us then is that 1.0093 tells me there is a 0.93% change between the minimum and the maximum values within the last 5. That's well under 5, and so we can use that bit of processing to justify that we have sufficient data for, in this case, Jetty Beach, so within this data set. We can then just copy that cell and put that under the other running mean. It will do exactly the same thing. In this case, we've got a little bit more variation, so this is 2.5% now, but again, we're less than 5, and so we can use that to justify that we have sufficient data within both data sets now. These would then be included in your summary table as part of your demonstration of sufficiency. Okay, so we now know we've got enough data. If these come out above 5%, so above 1.05, then you need to consider whether you've got enough data. Now, in this case, if you had 20 data points from each site, the default answer to that would be no, you don't have enough data. Get back out in the field, get some more. If you really do have a lot of data and it's unstable still, then it might well be that it is just inherently unstable, in which case that will be part of your evaluation. And that would certainly come into play if you'd spent more than a day out in the field getting results. Okay, so other processing we need to do. We need means for each of them. Whenever we calculate a mean, we're going to calculate a standard deviation, and then we're going to look at statistical significance as well. So mean, again, is really straightforward, similar to our running mean. We're going to have equals average, open a bracket, and then we'll just select all the data that we want to average out, and hit enter, and that's my average there. We want to do exactly the same thing for Castle Beach, the second site, and you can see we've got 2 means now, and there is a difference between them. Standard deviation is going to be a useful measure of how consistent the data are, and there's another formula for this. So this one is equals stdev.s. Now we're using .s here because this returns a standard deviation when you have a sample, and you have selected a sample of the population to measure. So stdev.s, open that bracket, select all of the data again, and it'll return your standard deviation in here. Again, exactly the same, copy that cell and put it over there, and that returns a standard deviation for Castle Beach. So in this case, we can see that Castle Beach has a higher average limpet height, but the data are less consistent because there's a greater standard deviation than at Jetty Beach. What we really want to know, though, is whether these 2 means are statistically significantly different, and that's what we're going to use a t-test for. Now, a t-test is going to return a p-value. P-value is just the probability that the 2 means are different due to charts. Right, so you want a low p-value to indicate statistical significance. So the formula for this is really straightforward. It's equals t.test. We'll open the brackets. The 2 arrays here are the 2 data arrays. So we've got the first data array at Jetty Beach, so select that, comma. Second data array is at Castle Beach, like that, another comma. Now, tails is whether you're looking at a 2-tailed or one-tailed t-test. That is a directional thing. So whether you're looking for a difference or a directional difference, we're just going to look for a difference. So we're going to go for a 2-tailed test. We can have a difference in either direction. In ecology, generally, we'll always go for a 2-tailed test. And the type, we're going to look for an unpaired one, right? Because paired t-tests are where you have the same individuals in both groups under 2 conditions. So that might be, for example, if you've measured heart rates before and after exercise in the same people. Here we've measured different limpets on Castle Beach as we did on Jetty Beach, So we're going to have unpaired tests. That comes in two categories, whether we have equal or unequal variances. We're not going to assume that we have equal variances, so we'll go for type 3. In truth, the differences between type 2 and type 3 are not massive, and you're likely to get the same result from both. So we'll default to 3. You can do a bit more digging into the variances if you want to. Close that bracket off and hit enter, and you can see we get a very, very small number in here. So this is 1.22 times 10 to the minus 5. And that's a very small probability that our data are distributed in the way they are due to chance. So here in my statistical testing, I would be rejecting my null hypothesis and accepting my alternative. Okay, now to graph this one, we're going to want to graph the means in our two sites, and then we're going to want to use our standard deviation as error bars on that graph. So to do that, we're going to have Jetty Beach. We're going to hold down control so we can select multiple cells that are apart from each other. So Jetty Beach, hold down control, select Castle Beach. Those are our two sites, and then we'll control click the means. So hold down control and select all 4 of those cells, and then insert. We're going to want a bar graph and a 2D column, and you can see that that gives us a chart like this. Now this is going to need some refining. We don't need a chart title. We do need this to be captioned in your write-up, but you don't need a title on the graph. This is rather irritating. So we're going to right click on the axis, format axis. We're going to come down to number, and we don't need decimal places in here, so we can just put 0 decimal places, and that'll get rid of those. We're also going to need axis titles, so this is where we're going to click the little plus next to the graph. We'll add some axis titles in there. These will need labeling. So we want the mean limpet height, and the units in there are millimeters. And then on the x-axis here, we're going to have our site, which is Jetty Beach and Castle Beach. We're also going to need some error bars on this graph to represent our standard deviation and give an idea of how consistent those data were. So again, a plus sign on the right-hand side, we're going to go error bars, and we're going to go for more options. That's going to give us these options on the right-hand side. Down where it says error amount, we're going to go custom. We're going to specify the value, and then we're going to specify our standard deviation. So we're going to click the little up arrow. It's going to send us into the spreadsheet. We can click the first one and then hold down control and the second one, and that will give us positive values. We need to do exactly the same thing with negative values because we want them to go up as well as down. Enter, and okay that. And you'll see now we have our error bars on the bar chart. So the smaller standard deviation represented by a smaller error bar on the left-hand side, and then at Castle Beach we had a larger standard deviation. So that's differences. That can go straight into your write-up. You would need a summary table in your write-up as well, and then this complete results table will go to your appendix. Okay, so correlations. Now, this is going to have a slightly different setup. This is my complete data table in here. You can see I've got a load of data in there. So I'll talk you through this setup, and then we'll go through what we would do with these numbers. Okay, so first things first, you'll notice that within this data table, we have inconsistent decimal places. That's not good. We want to have the same number of decimal places for all of them. Excel, you can do this really straightforwardly. If you highlight all of the cells, you want to have the same number of decimal places. And then you can use these two buttons up here within the number section to either increase or decrease the number of decimal places you've got. So if I decrease it there, they all go to 0 decimal places. If you've been measuring things in millimeters with a digital caliper, then your error will be plus minus 0.01 millimeters. It'll measure to the nearest hundredth of a millimeter. And so we can have 2 decimal places in there, or whatever is most appropriate. You can see, having adjusted that using those buttons, we now have decimal places. Even like here where you've got 12.0, Excel will now display the 0.0, which it wasn't doing before. Okay, now, so what we've got here is 8 different levels of our independent variable. So we've got height on shore here. We're going to be measuring the limpet width at different heights on shore, and we're going to see if they correlate. Within each height, we've measured, in this case, 30 different limpets. That's 30 times 8, 240 different measurements. That's probably about right for something like width, which is quite a quick measurement to take. But again, we need to justify that we have enough data. Now, because we're going to be looking at a mean of those widths within each height on shore, we can use a running mean to justify our sufficiency. So this is exactly the same as we did with the differences and the t-testing. So the running mean in here, we're just going to go sideways rather than downwards. So the same formula in here equals average. And then we're going to, in this case, want just to be averaging that single cell, so C3. We'll close that up. we then want to lock, in this case, row 4. So we want C to change to D when we go into here, but we don't want the column to change. Now in here, again, we want our first cell in the range to stay the same, and we want our second cell to be able to adjust. So we want to lock C in that first one, and then allow the second one to change as we go down. So I'll hit enter from there, it won't change. And then as we use, again, the little bottom right-hand corner of the cell, the drag function, we'll drag that over to the right-hand side. We'll fill all those cells by copying. And again, we're going to get this little error, which is mildly irritating, but we can get rid of it. And then you'll see, so this last cell is looking at the average of all of them. The cell before that is looking at the average of the ones up to that point, but not the last. So we're going to then copy these cells into every row of our table. So that will then calculate the running mean for each of the cells, each of the rows in our table. Okay. So we now have our running means calculated. We can then use the same calculation as we did with the differences to work out whether our running means have stabilized. So we want to divide the maximum number in the last 5 by the minimum number in the last 5, and we want to check that that is not greater than 1.05. So there will be a less than 5% variation within the last 5 means. So we're going to use equals max, open that bracket, and select the last 5 cells of the running mean, close that, divided by the minimum, so min, open brackets, same 5 cells, close that up, and hit enter. So again, you can see here 1.0116, so that's a 1.16% change within the last 5 running means, which is well within our 5% margin for error, so that's fine. We can use that to justify that we have enough data at the 1 meter height on shore. We need to do that for each of these. So again, bottom right-hand corner with our little drag and drop square, drag that all the way down, and you can see in all of these now we have a running mean stability calculation. The one that's closest to 5% here is this one. So we've got 1.043272. That was at 3.5 meters up on our shore. But again, we're less than 5%, so we can still use that to justify having sufficient data. So that's a very useful little tool to justify our sufficiency. Then we need our means and standard deviations. Now this is of the actual data, not the running mean, so we need to be careful which ones we select, but same formulae as we had before. So we've got equals average, open that bracket, and then all of those ones, make sure we get up to the end of 30 there, and enter that, and that will give us our mean for that row. Our standard deviation, again, the same formula as with the differences, equals stdev.s, because we're looking at a sample and not whole population. Open the bracket, select all the data points, close it up, and there we go, standard deviation 2.11 for those. Highlight both of those cells, and we can use a little bottom right drag and drop to complete every row in our table. So that gives us then our means and our standard deviations. Okay, now we want to be graphing this, right? So the graphing, we want to do our height on shore versus our mean limpet width, right? That is ultimately what we're trying to show in this investigation. So to do that, we're going to highlight all of our heights on shore. We're going to hold down Control because our cells are not together, but we need to select them both. So hold down Control and select the means, and then we're going to use a scatter plot to insert a graph. So I'm going to use this one without any line joining. You could use one that has lines joining point to point, but I think when you look at these data, that looks like a fairly linear trend to me. So I would say that a linear best fit trend line is a more justifiable line to add to that graph than one that is point to point. Ultimately, that's a judgment call. You've got to make it, but I'm going to go with that. So again, I'm going to get rid of my chart title because I'm going to caption this later in the write-up. And then I need to add the elements to this graph that it doesn't already have. So I'm going to add some axis titles. I'm going to add a linear trend line. So we're going to add plus sign and trend line. And the default for this will be a linear trend line. So we can just tick the button. If you want to explore other types of trend line, you can do. I would say it's very unlikely that any of the other ones will be appropriate for ecology investigations, but they might be. So have a little play around. If you're going to use a different mathematical trend line, then make sure you justify it. Okay, now we're going to need some error bars on here, right? Because we've been calculating averages, standard deviations, and there is error in both of our axes here, we're going to have bidirectional error bars. So you're going to have horizontal and vertical error bars. This will rely on you having worked out some uncertainty earlier on in your experiment, which you should already have done. So again, we're not going to use the default here. So we're going to go error bars, little arrow, more options, and then that will add us some error bars, but they're not going to be what we want. So first things first, the horizontal ones, these are going to be matched to the uncertainty value that you had for the height on shore in your write-up. Now you would have justified that individually. So if you've worked out, for example, that your uncertainty in your height on shore might be plus or minus 0.2 meters, for example, and you've justified that in your write-up, then you're going to highlight the horizontal error bars just by clicking on one of them. You're going to have a fixed value, and that fixed value is going to be your error for the height on shore. Now, whatever you've justified there is fine. Just put it into that cell, and the error bars will adjust accordingly. So if you worked out as 0.1, then look like that. Okay, so that's very straightforward. Now, the vertical ones, because this is a mean, right? So you've got mean limpet width on the y-axis. This is going to be a standard deviation. Right? So as we did with the differences, we're going to use the standard deviations for each of them. So we need to highlight the vertical error bars like that. We're going to go custom again, specify value, the positive error value, click on the little up arrow, and then we're going to highlight all of our standard deviations, enter, and then our negative ones, again, all of our standard deviations, and enter, and then OK that. And you'll see your standard deviations now up here. So you can see that our higher standard deviations down here, so we have 15.9, that was at 4.9 meters. You can see a big error bar there. That graph is now ready. That can go into your write-up again, make sure it is captioned. Okay, so again here, as with the differences, we're going to want to do a statistical test on this in order to make sure that our results are statistically significant. So again, we're going to want a p-value to be thrown out of this. And that p-value in this case is going to give us the probability that a correlation of this strength or greater would appear in a data set which is distributed randomly by chance. Now, in order to get a p-value from correlation, that's a little bit trickier than it is with the differences where we've just got one formula because it's not baked into Excel. So it's a little bit harder to drag it out. So what I'm going to do here is to simplify this. I'm going to get rid of all these raw data. I'm going to have a nice summary table, and I've done that on a separate sheet here. So I've got my heights on shore, and those are in meters. I've got my mean widths, which are just straight out of column AG over here. And I've added two columns, one for the ranking of the height and one for the ranking of the width. The statistical test we're going to do is a Spearman's rank. That involves ranking both of those things. Now, we don't need to do that by hand. There is a formula to do that. It's over here on the right-hand side. So rank.avg is going to return the rank of a number within a range, and it's going to return the average rank. Now, what that means is that if you had two means, for example, which are exactly the same, then it would return an average rank of the two, which is what we'd want to happen in a Spearman's rank. So I'm going to go equals in cell B2 here, equals rank.avg, open that brackets. The number we want to rank is this one, so the one next to the cell. The reference is all of the cells, so that's the range that we're ranking within. And then the order is either descending or ascending. By default, we'll just put in 0. It actually doesn't matter as long as you use the same on both sides. So we'll close that off. Now, we're going to want to copy this into other cells in a minute, and we want our reference range, so A2 to A9. We want that to stay the same. We don't want that to change when we copy the cell. So we're going to lock the 2 and the 9. So we'll put dollar signs in front of the 2, in front of the 9, and that means that range won't change when I now, again, use that little square in the bottom right-hand corner, click and drag that to all the cells, and that will give me my ranking. Now, obviously, because we've gone up in our heights on shore, it's just going to go 8, 7, 6, 5, 4, 3, 2, 1. So this is one of those rare occasions where it might have been quicker to do that by hand. But what we can now do is just copy that list of cells, pop that into column D, and that now is doing exactly the same thing for these cells within the range of the means. So having done the ranks, we can now go on to get our R value, which comes out of the correl function, which is this second over here. So our R value, we're going to go equals correl, open the brackets, and then our ranges, we're going to do this on the ranks. We want to see how well the ranks are correlated. So we highlight the first column, comma, highlight the second column, close it off, and enter, and that is our R value. Now, if you're familiar at all with Spearman's rank, you know that 0.95 is really a very strong correlation indeed. So we're already in a situation here where we pretty much know what the outcome of this test is going to be. In the social sciences, you can categorize R sometimes. And so there are different ranges that would qualify as a strong correlation. Really though, in biology, we want to be working out the p-value. We want to know what the probability is that our results are due to chance, and that's p-value is going to come out. Now, as I said, this is not baked into Excel. Thankfully, I've done the hard work for you. You can see this is the formula which will ultimately return your p-value. You can copy this formula from this spreadsheet, which is linked in the description. You just need to make sure it's referenced. So you're welcome to copy this formula. You need to reference it to this video, and then that's fine. Okay, so we're going to copy this text. We need to highlight it up here and copy. And then we're going to come to this cell. We're going to go equal and paste it. Now, there's a couple of things that we need to adjust in here based on where your numbers are on the sheet. So every time we see R in this formula, we need to replace that with our R value. My R value is in cell B13, so we just click on there. There's another one later on. There it is. And get rid of that. Cell B13. The other thing we need to replace are the data cells. So where it says data cells, we need to select all cells which contain the original data. So we'll just delete that. Again, we're going to need the control button in here. So I'm going to highlight this column, hold down control and that column to highlight all of my original data. I need to do exactly the same thing then over here where it says data cells, delete that, and then highlight that column, hold down control, highlight that column, enter, and that will give me my p-value. So my p-value here, 1 times 10 to the minus 8, again, very small p-value. We kind of predicted that from the fact that the R value was so close to 1, that this would be a very small probability. And if you look back at our graph, you can see the probability that that relationship is entirely random is going to be very low. And so we were always going to get a low p-value here. The more data you've got in here, the better. So that's the Spearman's rank. Again, just make sure in your write-ups, you do need to quote the formula that you're using. So you would need to quote this TDIS formula, and you'd need to explain what R and the data cells were in there. You don't need to explain the whole thing. So where each of these little sequences come from. You do though need to reference where you've got that formula from if you didn't create it, which you didn't. Okay, so that's the Spearman's rank. You've got your R value, you've got your P value. You need to quote both of those in your write-up. Okay, onwards to associations. So associations we'll do in 2 different sections, depending on whether you're going to be looking at essentially one species or multiple species. So there's a couple of examples of this. We're going to go with one species first, and then we'll look at what happens when we're looking at multiple species in an association. So in this case, we're looking at periwinkles, flat periwinkles, these ones were, and the types of seaweed on which they were found. So we've got 4 different species of seaweed, and then we've got other, just for sake of completeness. And then we've got a count on each of these types of seaweed. So we found 45 periwinkles on serrated rack, 38 on bladder rack, etc. Quick maths will show you that we've counted 100 periwinkles here and where they were. So first thing we can do here is to graph this. Actually, the graph is going to be probably the easiest part of this. So all we need to do is select the whole of our data set. So from each of the descriptors and each of the counts, insert, we're going to want a bar chart, and that one, again, we'll get rid of the chart title. And again, we're going to need to add now some axis titles. Now, we're not going to have any error bars on here because we haven't calculated any means. If you have calculated a mean, as in if any of these cells or if each of these cells contains an average of something, then you would be expected to be calculating a standard deviation and adding that as error bars onto your graph. So that's your graph. That can go straight into your write-up. In order to do the statistical testing here, so again, we're looking for a p-value. We want to know whether there is a relationship between how many periwinkles you find and where you're looking. In order to do that, we're looking at a chi-squared test. This is one which is on your spec, so you've done before. So to do that, we need, firstly, a total. So we're going to need totals in both these columns. That's a new formula, so equals sum will give us our total. We're going to look at all of those cells and hit enter. That's going to give us 100. Now our expected values here, chi-squared is going to compare the values that we observed against the values that we would expect to see if there were no association between these variables. So if they were randomly distributed between the different types of seaweed. Now, if 100 periwinkles were randomly distributed between each of these 5 seaweed types, then you would expect to find 20 of each. So this is a really straightforward set of expected values. It's literally just the total that you had divided by a count of how many conditions you had. If you want to do that as a formula, you can do. It's equals 100 divided by the count of how many data sets you had, which is going to return 20. You don't really need to do that as a formula. We can just put 20 into each of these. So this is one where I'll forgive you for not using a formula. The only thing I would say here is if you now go and change these data, so if you went and got more results, for example, you would then need to change your expected values. If you used a formula for this, so if I lock these ranges and then drag it on, we're going to get the same result in here. But now if I had found, for example, 15 on the bladder rack, you're going to see that all my expected values now change. And we should just use that as a check. If we've got the same total in both columns, that's a good indication that we have calculated this correctly. So in order to do chi-squared, all we're going to tell Excel to do is compare this column of data with this column of data and tell us what the probability is that we would get this set of numbers, given that this is what we would expect. And so to do that, we have a formula which is rather more straightforward than the last one, which is equals chi-squared chi-skip dot test, open the brackets, and then all we need to do is select the observed range, the actual range, comma, select the expected range, enter, and again, that is now our p-value. So 8 times 10 to the minus 13. So you can see there is a very small probability that these data are a result of chance. If I were to go through and start putting these closer to 22, which would be our expected value, so 22, 21, 34, 20, 21, you can see the p-value now getting pretty close to 1. So this would indicate that the probability of these data now appearing in a random distribution is 97%. So the closer you are to the expected values, the higher your p-value is going to be. Now, if you have multiple species, this gets a little bit more complicated in that you will need to have 2 results tables. So this is how I would set it up if I had 2 species or more. So this sort of experiment would be answering a search question, is the species of periwinkle associated with a type of seaweed? So are we more likely to find one periwinkle on one species of seaweed and another type on a different type? And so what you'd normally have here is maybe 2 to 4 closely related species and various sort of habitats maybe, and you'd have count data on each of them. The reason I've got 2 tables here is this gets a little bit now awkward if we start having observed and expected frequencies in the same table, because they'll be next to each other and it's easier to separate them out. So firstly, we can graph this, right? We'll graph our actual data. So just as we did with our one species, we're going to highlight the type of series we want. We're going to highlight the column titles here as well, because that's going to help it to understand what's going on. So column titles, highlight all the data, insert 2D column, and here we go. Again, Excel has done pretty much all the work for us. Get rid of the title. You can see it's color-coded, the flat periwinkle and the column periwinkle. We need to add our axis titles, and that graph again now is good to go. That can go straight into our write-up. Again, if these cells contain an average, remember that you would need to calculate a standard deviation for each of those cells and add those as custom error bars in the same way that we did for the differences in the correlations. Right, now in order to calculate the chi-squared test in this instance, we are now going to need a bit more out of our totals. So each of the total row and column we need to represent what's going on in the table. So this one is going to be equals sum, open the bracket, and select that whole column, close the bracket off. So we've got 100 in there, and then we can just drag that all the way to the right, just as we have been doing the whole time, to give me 100. And I've got a total of 69 common periwinkles, and then we need row totals for each of them. So again, equals sum, open the bracket, select my whole row. So there we go. So 169 is my grand total. That's the total from all of my counts. Now, the expected frequencies in here are going to be calculated from the totals that we just calculated over here. And the way this works is that the expected frequency in each cell is going to be the column total multiplied by the row total divided by the grand total. And that's going to give me an expected frequency in here. So for this one, I'm going to refer to it on this table over here. So the column total multiplied by the row total divided by the grand total. And you can see it. So my expected value in here then would be 33. I'm going to just divide to 1. Okay, now in this case, we're going to need to be locking quite a lot of different things to be dragging this around. It might be quicker to write that formula out each time. But if I do want to drag this across, then I want the B to change, but I want the D to stay the same. So I'll lock the D's with a $, like so, and then I can drag that across. And then to drag it down, I want to lock row 8, but I want to allow row 3 to change. So I'm going to $sign the 8, and I'm going to allow row 3 to change, and I'm going to $sign this 8 over here. Do the same thing on this one. So $sign the 8. And then if I drag those down, that will not activate my expected frequencies for all of these cells. So we're pretty liberally using the drag and drop here. If you want to do this by hand, just because the $signs are getting a bit hectic in here, then you can always just click in this formula and make sure that you refer to the right 3 cells for each one. This is a quick formula to put together, so you can do that by hand if need be. The check that you can do in here is to copy the total formulae into the right-hand table, because you'll copy the formulae, but what you should get is exactly the same numbers. So we're now looking at the sum of these two, and it should be the same as the sum over here, and you can see that it is. And then again, if we copy the total columns down there, then we get the same numbers. So that's just a bit of a check. You don't really need these, but they should exactly match the observed totals on the left-hand side. So we've got expected values in here, we've got observed values over here. Our chi-squared test then is exactly the same. And we're just going to go equals chi-squared dot test, open the bracket, select my actual range, so my observed range, comma, select my expected range, close the bracket off, and there we go, 8.59 times 10 to the minus 10. So again, very small probability that this distribution is due to chance. So I would reject my null hypothesis and accept, in this case, the hypothesis that there is a significant association between these two variables. So that's that. There you go. Use each of those as you will. There's a link in the description down below to a version of this spreadsheet that has both completed and blank sheets, so you can play around and use what you need. But make sure if you are using a formula which isn't standard, that you're referencing it. Otherwise, enjoy your bio, go well.